Our trapezoid rule proof. Wait, how do I? Okay. There we go. 1 second. Okay, so we'll start with the trapezoid definition. So a trapezoid is just anything that is a rectangle that has two triangles that are essentially complementary. So something like this. Or you might see this, where they're complementary. And we'll label H, A, and B. So much like the Riemann sums of right, left, and midpoint, which all use rectangles, there's a new one defined as Riemann sums, Riemann trapezoidal sums. So there are actually 4 types of summations. And the proof is as follows. So the formula is 1/2 A plus B times H, where H is, or no, A plus B times H? Yeah. So instead of using it in this configuration, we will use the approximation. We'll flip this 90 degrees, and we'll use this as H, B, and A, H, B, A, H, B, A, where A includes this subsequent line, and B only includes this top part. So the formula is as follows. A equals A plus B over 2 times H. But remember, H was that bottom part that we mentioned. So it looks like this. This is B, A, and H is here. So H can be defined as delta X, which, as everyone knows, is B minus A over N, depending on the amount of partitions you want, or not the amount of partitions, because a partition is just including all the intervals of between the 2 points, all the intervals between the upper and lower bound that you want to describe it as. But it's more accurately defined as a uniform subintervals, I guess. It's probably the logical way to say it. So we use this formula. Well, to mathematicalize it, we did it here, and we do it here. So let's take a curve, and let's say it looks like that. Then if we set it equal to that, where we're using trapezoids to approximate, then this will be f of x of I, and we say I because of the iteration. Actually, that's and that will be f of x of I plus 1. Or if you want to get technical, you can define it the other way around. And this is, I don't know why you would ever use this when you can just integrate. But I guess this is just something you have to learn for calculus. You can do f of x of I and f of x of I minus 1. So logically speaking, the area formula for any trapezoid is going to be f of x of I minus 1 plus f of x of I plus 1 divided by 2 times delta x. So if you do the summation of that, much like you can pull out the delta x of anything, you can actually put out delta x over 2, which is constant, times f of x of I, or f of x of 0, which is the first starting point, so whatever the first one is, plus f of x of 1 plus wait, f of x of 1. Oh, sorry. And now you just have to do the subsequent triangles. But actually, before we do that, let's just define the idea here. So then that would be f of x of 0 for the first triangle plus f of x of 1 divided by 2. And then the next one is going to be delta x over 2 of f of x of 1 plus f of x of 2 over 2, and so on and so forth, all the way until f of x of I, or actually I forgot to put the delta x, minus 1 plus f of x of I divided by 2. Well, math is just logic, and you can see that every point is repeated except the first and the last. So you can rewrite the area of the trapezoid formula as delta x over 2, because you can factor that out of every one, and f of x of 0 plus 2f of x of 1 plus 2f of x of 2, and so on and so forth, all the way until f of x of I. So it would be area equals delta x over 2 of f of x of 1 plus f of x of 2 plus f of x of 3, except these are 2's, plus f of x of I, which should be the formula here. And that is the proof here. It's just simple summation and factoring out the delta x over 2. The reason for you using this, I mean, it's not very clear, but maybe like somewhere down the mathematical history, what is it, Riemann forgot to, or didn't forget to, maybe didn't have the fundamental theorem of calculus yet. I mean, he was. Wait. And but he did though. 'Cause he was born in the 1800s.